Last time what was we discussed was fourth video, right? I hope you have seen the fourth video. If you have not still watched that video, go and watch what I can say now. So I'm just revising the thing that I have done in the fourth video. We talked about statistical averages and the definition, how we define them. So there are infinitely possible statistical averages, but the point of interest, random variables that we are going to use a lot. There are only not random variable, but statistical averages. So there are only 5 statistical averages that we are going to look into, and that will suffice our analysis in communication engineering. So statistical averages we can find if I have only one random variable, and it may be like I have function of that random variable. So we know that when we fix the time, we get a random variable. So this, when I'm writing this xt, here I'm assuming this t is a specific time. So I'm fixing it. You can write t1 also if you want. So this is just a specific time. But till this is one random variable, I don't have to write t1, t2 like that. I can write simply this is just a specific time. At a specific time I'm talking here, right? Because it's not a random process. Whatever goes inside this expectation, it should be a random variable. So it has to be random variable, and to be random process, to be a random variable, it has to be sampled out at one time, right? So this is just a specific time. And what we know is the PDF of that random variable at that time. So at that time, I know the PDF of that random variable. But what you see here, this fxt x, fx x comma x, I can write this as a function of time explicitly. So these notations are same. And we say that when this is a function of time t. So this is a function of time t. So whatever you derive from this PDF, that in general going to be function of time t. So this is called statistical averages. When you write expectation of gxt, this is nothing but statistical averages. So how many function you can define on xt? I will say infinite possible function I can create as a function of xt. So there will be infinite statistical averages, right? This is simply defined as wherever that this will be g of small x, because it has to be numerical value. So it is just a point, means when you fix omega, when you fix time, you get a point. So it's just a point. This is the PDF at that time, and this you can simply write like this expression. So this is simply same thing I've written in the second line also. So in general, this is a function of time. So this is a function of time. So the entire thing in general going to be function of time. It may be, it may not be, but in general it has to be function of time t. So this is what the statistical averages are now going to be function of time t. In case of random variable, there is no concept of time. So their statistical average has nothing to do with time. But in case of random process, whenever you looked at any particular time, you and calculate the statistical averages, and you fix at another time, you get and you find the other statistical averages, you will find that these statistical averages at t1 are not same as statistical averages at time t equal to t2. That is the meaning of dependency on time. Now we saw three function of xt. One is simply xt. So here g of xt is simply xt. Here g of xt is x squared t, and here we subtract mean from this xt. So this is xt. This is not x, this is xt. This is xt. So you subtract the mean from the random variable. So you will get only AC component, and you square it. So you're getting the power in AC component. So this is power in AC component. This is total power, and this is the DC value. And when you square it, you will get DC power. All these three parameters are the examples of statistical averages. Not only this are statistical averages. So when you make x cube t and take the expectation, that is also a statistical average. So that's why I'm saying there are infinite possible statistical averages, and those all statistical averages will depend on time t. But here we are going to talk only on these three, which are important: DC power and AC power. They all going to be function of time t now. So simply xt will be simply x, because you have to replace by gx. So this gx is nothing but capital X, so it has to be x, and this is again a function of time, so it has to be a function of time t. So people write it either you can write mu suffix x of t, or you can write mu suffix, and then I can purposely write this mu x is a function of time. So you write in bracket. So I hope this notation is clear. You may write it like this, or you may write it like this. So here you are saying explicitly that mean is a function of time. Similarly here also, and the variance also. Okay, so these are called variance, AC power, and we know that when the total power has to be equal to DC power plus AC power. So this is how these three parameters are related. If you know two of them, you can find third one. You don't have to use the integration and all those things. So these are the formulas for one random variable, and if you generalize it for two random variables, I have already talked on this. So you sample the process at 2 times, let's say t1 and t2, you get two random variables xt1 and xt2. So you can have any function of xt1 and x2. So again, there are infinite possible function of these two random variables. So how many function I can define? I can define infinite function, infinite number of functions on this two random variable, right? So when you have two random variables, you have to talk about joint PDF of these two random variables at the same time. So this xt1, this is joint PDF of xt1 and xt2. When xt1 takes x1 and xt2 takes x2 value, numerical value. So again, I can write it in this notation, that this is a random process x1 and x2, and this random process is sampled at t1 and t2. So this is again, I can say this joint PDF is going to be function of time t1 and t2 in general. It may not be, but in general it has to be function of time t1 and t2, right? So this is what the joint PDF. So there we are using only single order PDF. Now it's a double order PDF. Now again, I'm doing the same thing, that I will take this expression of g of xt1, xt2. I have two random variables. I need two integration, and I need second order PDF. So this is second order PDF, and simply it will be g of x1 comma x2. So you have to replace wherever this x, you have to replace with x1 and x2. This is as simple as that. Now again, this has to be function of time t, and this is nothing but statistical averages when you consider two random variable. Statistical averages when you have two random variables. So I can have infinite statistical averages of two random variables, but the most important statistical averages are autocorrelation and autocovariance. Auto is something what when you have the two random variables from the same random process, and auto covariance is something, again, auto means what, you are having the two random variables from the same random process. If you have two random process and you are taking one random variable from one random process and second random variable from the another random process, then and you multiply them and do the expectation, you are going to call that as a cross correlation. Co means two, right? Okay, so this will use two integration. This is just a product of two random variable. So it will take x1, xt2 will take x2, and this is the joint PDF that I'm using here. This is written as in the notation wise. It's what rx t1 x t2, and explicitly you can write this autocorrelation as a function of time t1 and t2. So this is r suffix x t1 comma t2. So here it is again what all the statistical properties are going to be function of time t in general, right? So this t1 and t2. So both time, at what time you are taking this product of this two random variable, those time will come into the picture, right? So they definitely change these parameters. Now variance is defined as what you have random variables subtract the mean. So covariance is also same thing. It's very much similar to that. You have random variable at t1, subtract the mean at that time t1, and then you have random variable at time t2, subtract the mean of that random variable at time t2, and multiply them. You get you take the expectation, you call it auto covariance, because again these two random process are these two random variables are coming from the same random process x of t. So this is again fairly simple. You can just replace capital Xt1 with x1, and mu xt1 is just a value, so I need to just subtract it from this x1, and then same thing here, and you can write this joint PDF. Double integration has to be there. Covariance is denoted by capital C, xt1 into xt1 and xt2. So it is simply written as cx t1 comma t2 to show that it's also a function of time t1 and t2. So this is function of time of t1 and t2. I hope this makes sense. But I can define so many function of xt1 and xt2. So these are only two functions that we need to read that will suffice our analysis. So this is what gxt1. This is one kind of example of this gxt1 comma xt2. This is an example of again gxt1 comma xt2, which simply uses this formula, right? So you have to remember this formula, and you have to understand when you multiply these two, you get autocorrelation, and when you subtract the mean from each random variable and then multiply them, then you will get autocovariance. So this is the thing. And similarly, when you have total power, when you plug t1 equal to t2, you get mean square value, because we are talking about the two random variables at the same time, means you are talking about the same random variable. So this will simply becomes, when t1 is equal to t2, it becomes mean square value. So mean square value is a special case of this autocorrelation. Similarly, covariance, in covariance, if you plug t1 equal to t2, means same time, you can get only one random variable, and this becomes simply square of this, so this becomes variance. So variance is a special case of covariance, and mean square value is a special case of correlation. So in the same respect, here it was mean square value, I have written correlation. Instead of AC power, I have written covariance, and this is simply what mean of product of individual means. So this is how this relation is true. So when t1 is equal to t2, this becomes expectation of x square t, that is equal to t. And similarly, if t1 is equal to t2, then this becomes mu x t square. And when you take t1 equal to t2 equal to t, in this one you get simply variance. So that is what variance of square. So again you get back your original form, that is what this form. So two random variables, you can always get back to one random variable. You can generalize it for any number of random variable. You can have xt1, xt2, xt3, then you need triple integration, and this PDF will be third order PDF in that case, and it will be function of x1, x2, and x3, and this will be dx1, dx2, and dx3. And you can define again any number of statistical properties, but we will not go into the third order, and we don't require them. So there we talked about correlation. So correlation, when you say correlation, so this is the correlation depend on t1 and t2. If it is 0, then we say this xt1 and xt2 are orthogonal to each other. And when you take covariance cx t1 comma t2, if it is 0, then we say that xt1 and xt2 are uncorrelated, which is linear independent. So uncorrelated is something what linear independency. So this is what the meaning to this. And one more thing, when one of the mean is 0, if mu xt1 is 0 or mu xt2 is 0 or both are 0, then correlation becomes simply covariance. So that I want to write here. So when mu x t1 is 0 and or mu x t2 is 0, then correlation, autocorrelation is same as autocovariance, that is t1 comma t2. So I hope I don't have to write this name here, but it is suffice to say that it's a what it is called as auto correlation. I am using it word this again and again. So this is autocorrelation and this is called auto covariance. So in general they are the function of time. This is what that we studied last time, and independency is rather more strict condition than uncorrelatedness. So independency simplify your life. So independency simplifies the analysis. So what is the independency meaning is if xt1 and xt2, it may be for 3 random variables also, if xt1 and xt2 are or let me write are said to be independent if and only if that joint PDF of this is simply the product of individual PDF. So x1 comma t1 and fy y1 comma sorry not y but it's x2 comma t2. So if the joint PDF is multiplication of individual PDF, so then we can say these two random variables are independent. It's a rather more strict condition than the uncorrelatedness. So independency it implies uncorrelatedness, but the reverse is not true in general. So this reverse is not true, right? And one more thing, if you have independent, if xt1 and xt2 are independent random variables, so you can use this equation and then you can prove that this autocorrelation xt1 times xt2 is simply becomes expectation of xt1 times expectation of xt2, because if they are independent then they are also uncorrelated. If they are uncorrelated means the covariance is going to be 0. So this says uncorrelated is what, when covariance is 0. So this is independent है तो covariance 0 होगा. If covariance 0 होगा तो AC power वहाँ पे मतलब AC term होगा ही नहीं. So this will go to 0. So if the random variables are uncorrelated, then so you can say if they are independent or uncorrelated. So whether they are independent or uncorrelated, it makes what covariance t1 comma t2 to be 0, and in that case this will contain only this product of expectation. So expectation of product is nothing but product of expectation if xt1 xt2 are independent or they are uncorrelated. If you say me uncorrelated also, then also I will say the covariance is 0. You can see here the covariance is 0, then we say that they are uncorrelated, right? So this is like this. So uncorrelated means covariance is 0, covariance 0 means uncorrelated. So uncorrelated does not imply independency, but independency does imply uncorrelatedness. So if they are independent, then covariance will be 0. So the covariance can be 0 whether they are uncorrelated or independent. So this is what the thing is. Now uh, uh, here we are going to talk about the classification now, right? So let me talk about this first classification, which is called as WSS process. I have already explained it in your that fourth video. So WSS random process. So this is one of the classification. WSS stand for weak sense stationary process. Some people call it wide stationary process. Weak sense means what? It is rather less restricted condition than the strict sense stationary process. So wide sense stationary process, so a process, a random process is said to be WSS if and only if mean, if you calculate the mean, that is mu xt will be constant. So we are denoting it is not dependent on time, so it's a constant. And so both must be true. And this autocorrelation, that is Rx t1 comma t2, or you can say this is expectation of product of these two times, that is xt2, is only function of time difference. So this will you will get as a function of time difference either this way or this way. It's a time difference, right? So it's a constant independent of time. Independent of time means it independent of absolute time. So independent of time. And when you say this, then it is what? Independent of time. Or you can say it only depends on the difference of time. Only depends on difference of time. So sometimes what they say, this thing, if you see, you can take t1 as t and t2 as t plus tau. So they call it, you sample the process at t, and after you sample the process at t plus tau. So this is called time difference, or you can call it time shift. So this is shifting parameter, time shift or time difference. So this expression I can write this as a Rx, then this will be Rx t1 comma t2 will be simply Rx t, and t2 is t plus tau, so this will be t plus tau, and it should be the difference of these two. So you can see this t2 minus t1 is tau, so this will be only tau, and this is same as Rx minus tau, because you can take t1 minus t2 or t2 minus t1. So it means that one autocorrelation of a WSS process is an even function, right? So this sometimes people start with this, they choose t1 equal to t, and they choose t2 equal to t plus tau, because I can choose any t1 and t2. This should be true for all time t1 and t2. So this is true for all t1 and t2. For all t1 and t2. So I am free to choose any value of t1 and t2. So I have chosen, this is my choice, because this equation has to be valid for all time t1 and t2. So I will choose t1 as t and t2 as t plus tau, because I can choose any time, right? So this is what I have chosen. So this is called WSS process. If you see that example, numerical 5, which I have taken on this numerical video, that was what xt was there, and there we have a cos 2 pi fct plus theta where theta is uniform random variable over some range, suppose minus pi to pi. So if this is in the range in the multiple of 2 pi, then we got the mean value expectation of xt, which is mu xt. हाँ कितना मिला था अपने को? 0 मिला था, right? And 0 is nothing but a constant. So no matter at what time you look at the random process, the DC value is always 0. It means what? DC value is constant, and in this case it's a 0 at, or you can say at all time. So the DC power is going to be constant, is going to be constant, and in this case it is 0 watt. I can write 0 watt. This is 0 volt. I can say this is 0 volt. If I write this is a 0 volt, and this is a signal which is voltage. So this is the with respect to example I am talking now, right? But it is in general. If this mu x is constant, so it is mu x which is constant. So DC power is going to be constant. Okay, good. Means no matter at what time I am going to look at the random process, the DC power of random process is always constant. It's a good for me. It is going to simplify my analysis. At least power is not changing with respect to time. अगर ऐसा होगा कि नॉइस इस टाइम पे इसका पावर कुछ और है, नेक्स्ट टाइम पे कुछ पावर इसका कुछ और है, देन इट इज going to be rather complicated situation as compared to if power are constant. And there we have part 2. We discuss the numerical as expectation of xt1 xt2, and we called it autocorrelation Rx t1 comma t2, and there we got this as a square by 2 cos 2 pi fc t2 minus t1. You can write t1 minus t2 also, because we know that when this is cos is even function, so you can write t1 minus t2 or t2 minus t1, both are same. So again this is again what this is come out to be Rx, and the difference of time, it may be t2 minus t1, or it make a thing this is a only the time difference. So you can see that one, this is only time difference, and if you choose t1 as t and t2 as t1 plus tau, you will simply get this as what? Rx function of time difference, because this t1 minus t2 or t2 minus t1, it will be simply Rx tau, and in that case I am talking about this is, it is just a matter of fact that notation, right? Notation, some books write it like this. So they choose time purposely t and t plus tau, right? So they choose t and t plus tau, right? So this is t plus tau, and it is only the sense. You can say this is only function of time difference. So I can say it does not depend, this autocorrelation. So this is what a square by 2 in example, a square by 2 cos 2 pi fct fc tau, t2 minus t1 is nothing but tau now. So both are same. You say this or this, both are same. The thing is tau is only time difference. So you choose two random variable at two time, but the autocorrelation, it does not depend on at what time you have chosen. It only depends what is the time difference between these two random variable. So it means it is independent of absolute time. It only depends on what? The time difference. So that is the meaning of this function of independent of time. So autocorrelation is independent of absolute time, right? It only depends on the time difference between two random variables chosen. So time difference between chosen random variables xt1 and xt2. So you can also say that this autocorrelation is independent of time origin. So this autocorrelation is independent of time origin. Right. What I mean by that, if you have random process, I can have random process like this. I will have collection of sample functions. So let's say three of them. And when you see two random variables fixing at time t1 and t2, and you take another two random variables fixing at time t1 and t2, t3 and t4, and what do you see here? Suppose this is at t1 and t2. Two random variables I have chosen at t1 and t2, and two random variables I have chosen at t3 and t4. Suppose this is 2 second, let's say this is suppose 4 second, let's say this is 8 second, and let's say this is 10 second. What you find here is very simple thing is what this difference is 2 second, this difference is 2 second till the time difference is same. So this is xt1 and this is xt2. So these are the values of this xt1 and these are the values of xt2. So this is a random variable xt1 and this is xt2. This is xt3 and this is xt4. But what do you find here? This rx, let me write this with the red color, rx t1 comma t2 will be exactly same as rx t3 comma t4 because t2 minus t1 is exactly same as t4 minus t3. So it does not depend on the time origin at what time you are choosing, but it depends on the two random variable at what separation you have chosen. So that is the meaning of WSS process. And finally, what we saw was mean square value is just a special case. I'm just repeating this sentence again and again. It's a special form, a special case of autocorrelation Rx t1 comma t2. This is mean square value, which is x squared t. The special case of Rx t1 comma t2. And what is the special case? Is this Rx t1 comma t2 will be expectation of x squared t, or rather I should write the definition of Rx t1 t2. So this will be more easier to see this one. So when you choose t1 equal to t2, and let's say this is t, you get this as a mean square value. So if you know autocorrelation, you can find mean square value. So the third example that we took in that numerical, or the third calculation which we have done, was calculation of mean square value. So mean square value is going to be expectation of xt1, xt2, and take t1 as t1 same as t2, and you get the answer. So what we got was a square by 2 cos 2 pi fc, and that was t2 minus t1. And when you plug t1 equal to t2 here, what you get is going to be 0, and this cos 2 pi cos 0 is going to be 1, and in that case this will be just simply a square by 2. So this is the mean square value, which is total power. So you can see this total power is constant if you say Rx is only function of time difference. So this come out to be constant. So what we got, this is part C that we did in the numerical. This was part B. Check the calculation part, go and how I did that. So I'm not going to discuss it again. From part A, I can say the DC value is constant, so DC power has to be constant. From part B, I can say the mean square value has to be constant because it's only function of time difference. So what I can say this as what, this is simply Rx 0. Why I'm saying Rx 0? Rx is only function of time difference, tau, Rx tau, kidhar gaya Rx tau? So this is, right, when you take T1 and T2 same, then tau has to be 0. So sometimes people also say this same thing here in this. They don't write xt and xt2, but they write what? Expectation of xt, and they write expectation of xt plus tau. So when you choose this time same as this time, then you are saying that when t plus tau should be equal to 2, this means tau is 0. So you are saying tau is 0, you get this one, and this is nothing but rx tau, because it's only function of rx. T1 and T2 both are same, right? So this is Rx tau. This is Rx tau. So Rx tau equal to 0. So Rx 0 will give you what? Rx 0 of WSS process will give you mean square value. So here the formula is, so if you plug tau equal to 0, you get, it will be a square by 2. T1 is equal to T2 means tau is 0. T1 is equal to T2 means tau equal to 0. I hope this is making sense over there. So when tau equal to 0, you get mean square value. Total power is constant. What I find here is this one. You tell me DC power is constant. Total power is constant. What about AC power? Will it be constant or not? Since DC power is constant, total power is constant. What about this AC power? Will it be constant or not? बोलो भाई, टाइम नहीं है. What is the formula of total power? Total power.
Yes, it will be constant.
It will be constant, right? Because total power is equal to DC power plus AC power. और उसमें से दो लोग constant है तो तीसरे वो constant होना ही पड़ेगा. So this is nothing but total power minus DC power. So if this is constant and this is constant, and in this example, if you see in the example, which is a square by 2, we got a square by 2, and DC power we got as, so this has to be a square by 2 in this particular case, and in this particular case AC power is equal to total power also. But when you say, the moment you say the process is a random process, so let me write that. The moment you write if the WSS, if the random process is WSS, then all the power are constant independent of time. Constant independent of time. It's good for me. Random process is there, but at any time I check the power, DC power, AC power, total power, they all remain constant. They are nice buddy, right? They are always constant. So they are not going to create problem. They are not changing with time if the process is WSS. So you can see this is the just result you can conclude from WSS, that all the power has to be constant independent of time t. Now this is the next part which I have not done in that numerical. This is part D. This is related to power spectral density. So PSD. So PSD is defined, PSD for random process or anything, it can be defined as a Fourier transform of autocorrelation function. So for WSS process, this is only dependent on tau, time difference. So it is only Fourier transform of what? Autocorrelation function. And we know the Fourier transform formula, it will be from -infinity to +infinity. This will be Rx tau. We can just think this as this is a variable. We don't have t here, we have tau here, right? Why I'm saying tau here? Because it does not depend on the absolute time. It depends on only what? Time difference. So time difference is different than the absolute time. So the Rx tau e power minus j omega, now it is tau. It's not t, it's a tau, and it has to be tau. So check these things, right? So this is a Fourier transform, and Rx, so I can say this SXF is just make the Fourier transform pair with, let me write on this side, this thing I should write on this side. So Rx tau Fourier transform जो होता है Rx tau का, वो power spectral density होता है, right? Let me quickly find that for this given problem, as Rx tau is a square by 2 cos 2 pi fct plus no t2 minus t1 and t2 minus t1 is nothing but tau. So the Fourier transform of this, अभी मैं रिपीट नहीं करूंगा क्योंकि इस कोर्स के 10 लेक्चर में मैंने बस फूरियर ट्रांसफॉर्म ही पढ़ाया है. सो दिस विल बी a स्क्वायर बाई 2 into 2 because cos 2 pi fct will be del f minus fc plus del f plus fc by 2. So that's why this 2 will be because of this fact. So you get two impulses at f equal to fc and f equal to minus fc. I can plot this PSD. Let's plot them. Let's plot them quickly. So I get two impulses at f equal to minus fc and at f equal to plus fc with the same height. So this is at minus fc, this is at plus fc, and this is a square by 4. The amplitude is of this impulse is a square by 4, and this is called the PSD versus f. For line coding we have seen, for this particular example it's two impulses, and what is the power? I can calculate the total power from here also. So I can calculate the power, total power. So power can be calculated. So total power is going to be area under PSD. So it should be area under PSD. So this is area under PSD. So when you integrate impulse, you get 1. So you'll get a square by 4 for this area. And when you integrate this one, you get an area of a square by 4. So this will be exactly equal to a square by 2, no matter what. It has to be, because we already calculated the total power as a square by 2. So यहाँ पे भी a square by 2 आना ही चाहिए. So this is nothing but random process का mean square value. So power you can calculate by this. Either you can, this power you can calculate, either you take tau equal to 0, or you can find the area under PSD. This is what the total power can be calculated. This is total power. This is not DC or AC something like, but it's a total power, because power spectral density is just a density. So the given problem that I have chosen was an example of WSS process, right? Okay, next thing is what, let me write triple S process. This is a second classification. Triple S, or you simply call as stationary process. Stationary process, random process. So this is not this is something what a strict sense stationary process, right? So when you say strict sense stationary process, you define it like that one. I like this, that statistical properties should not change with respect to time. So statistical properties do not change with respect to time, right? What do you mean by that? How many statistical properties you have? How many statistical averages you can define?
Infinite.
Infinite. So how many conditions you need to check to prove that this process is strict and stationary process? Yes.
Infinite.
Yes. So since there are infinite statistical averages or properties, so I need to check infinitely many conditions to prove a random process to be stationary process or triple S process. So nobody can do that. Nobody can do that. Nobody, right? But by the intuition, you can come to the conclusion that yes, it is a strict sense. After doing 20 to 30 statistical properties, you may come to the conclusion that अरे यार अब change ही नहीं हो रहा है, तो कोई भी ले रहा हूँ मैं function ले रहा हूँ कोई भी, I'm getting the same constant independent of time. So this is the meaning of this. This is the meaning of this. This is very, very restricted condition. That's why you're calling it a strict sense stationarity process. But if you go back and check here, WSS process, it says that one, bhai ab do hi check kar lo. Which one? Mean and autocorrelation. You check mean, it should be constant. You check autocorrelation, it should be time difference. Then I can say this is WSS process, which is weak sense stationarity process, in which you are requiring only two conditions to be satisfied. One is the mean and one is the autocorrelation. But if you see the result of these two, you get very, 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 very powerful simple analysis can be done, because the total power are going to be constant. AC power, total power, DC power, all the constant. PSD is very wonderful. It's not going to change with respect to time. Anytime you see the spectrum of this random process on DSO, you will find that one, this is same, because PSD is going to be same. So because it's independent of time, right? So those properties, now check this condition. So people started defining it like this one: first order stationarity process. First order stationary process. First order stationary process. So first order uses first order PDF, that is fx x comma t, right? So this is what the first order PDF. We just to be this is very simple to understand. What was that statistical properties of G of one random variable? It was what? I've written everything in the previous slide. This is minus infinity to plus infinity, G of x, fx, x comma t dt. So on the basis of first order PDF, I can define any number of function, infinite number of functions. So if this is constant, independent of time, because we are saying in general it's a function of time. If it is constant, independent of time, so I can say this integration will be constant. So all the statistical properties which are related to this fx xt, including this mean value, mean square value, whatever it is, DC power, AC power, they all are related on the first order PDF. If the first order PDF itself is constant, so any function of x of t you will take, since this is dependent on only this parameter fx xt, which is constant independent of time. So you can see this first order, all the properties are going to be independent of time, which are going to be constant, including DC power, AC power, total power. You can choose gxt like this also, like x cube t. Oh, you can choose, but it's going to be constant, because you're saying that in the integration term, which is dependent on time, that term is already constant. So x cube t का भी अगर आप expectation निकालोगे तो भी क्या मिलेगा आपको? constant मिलेगा, if this is constant. So we are saying that one, that no matter at what you look at this, let me choose this as a t1, and this should be exactly at t2. So at t1 पे आपने चेक किया तो PDF मिलेगा, अब t2 पे चेक किया PDF मिलेगा. If they are equal, then you can say the first order stationarity process is going to be there. The process is what? First order strict sense stationary, you can say. So this is for all t1 and t2, for all t1 and t2. Why I choose this? So my choice will be what? My choice will be this one. My choice will be t1 will be t, and t2 will be 0, because you are saying me that when it is true for all time t1 and t2. So my choice is t1 is equal to t and t2 equal to 0. If I plug that one, I can come to the conclusion that this is x t and this is fx, and t2 have you replaced with 0 time, so it does not, t is not going to appear in this expression. So you can see that at any time you can see the PDF, this will be only this is not going to depend on the time. So this is what? Constant, or you can say this is independent of time. So single order PDF is time t. So this is the meaning of independency. It does not depend on the time. So if I choose t1 or t2, it should be same. That's why you are saying this should be independent of time. So I've just followed that your rule, and I've put my choice. I can choose any t1 and t2. I choose this one. Why not? I can choose this also. Now, so all the properties related to first order PDF, they are going to be constant. So it means our DC power, our AC power, because they are defined on the one random variable, and the total power, they all will be constant. Why this only? this also going to be constant, this also going to be constant, because we are saying that PDF is constant. If I can any function of this, it should be constant, it should be not depend on time. But here what I chosen this DC, I am just concerned about this one, right? This is why this is strict sense. Now if you go with this one, second order, what is the second order? The stationarity process, or let me write triple S process. In general, it should be infinite order stationary, right? But we are just talking about first order, second order, and all those things. So it is saying me that one that if I choose second order PDF, so I need to choose two random variables. So this is x1, x2, and the time will be definitely t1 and t2, but it should be time invariant. So this would be x1 comma x2. So if I shift my t1 with tau and t2 with t2 plus tau, I should get same thing. So t1 I shifted by tau and t2 I shifted by tau. The PDF should not change. So this joint PDF should not change. So what is the meaning of that? Is simply, I will come to that point again. Okay, so this should be true for all T1 and T2. We are saying T1 and T2 for all T1 and T2. Why I'm going to take T1 and T2? My choice will be what? My choice is T1 is T and T2 is just let's say T1. Let's say this T1 as minus tau. T1 is minus tau, and T2. Let's say it is what I should choose. Let's say choose it's the T. Right, I've chosen T. What I get then? Okay, I need to choose some different number. Let me, this T1 is minus tau. Let me choose not T1, T2. Let me choose T1 as minus tau. T1 as minus tau. T1 as minus tau. This will get cancelled. T2 as 0. Let's say T2 is 0. T1 is minus tau. And let's put this number. I am just thinking on the situation how to prove this one, right? So that's why I'm choosing, I'm not only choosing on randomly, but I'm choosing properly. So this is what T1 equal to minus tau y. So this will be T2 equal to 0. I'm choosing this number. I will just choose T2 equal to 0. I don't need to choose this one. T1 equal to T. Let's choose T1 equal to T or not. T1 I need to choose minus tau. Otherwise I will be in trouble. So this will be what T1 is minus tau. It's not working. I need to get T2 minus T1 here. So if I choose T2 T1 as 0 और T1 T2 रहने देते हैं इसको. Okay, ठीक है. Let's see this what we get. So it is just let's say T1. Let me choose this. What I can choose a good number. T1. Let me write that first. Then I will see that what I should choose. Or you will tell me what side I should choose. This is 0 and this should be T2 minus T1, that is tau. What should I choose? What should I choose to get this one? T1, T2. To make 0, you need to choose tau, T1 equal to minus tau, that will be 0. And T2 plus tau. Okay, that's correct. This is correct. So I need to choose T1 equal to minus tau. So T2, this will give me T2 plus tau will be T2 will be tau is minus T1, so this will be T2 minus T1. So it will only depend on tau. So this is, I'm not doing anything, something what I need to prove it, right? This double order PDF only depends on the time difference. So you can see, so this fx joint PDF x1 comma x2 T1 T2, it is not dependent on T1 and T2, but it depends on what? Only their time difference. This is what the meaning is. So this is, in the sense, it is independent of time, independent of, you can say, absolute time. So it does not depend on the absolute time, but depend on depends on T2 minus T1, or time difference. It depends on what? Time difference, tau. It depends on only tau. So all the properties like autocorrelation, cross correlation, they all depend on the what? Tau. I hope this makes sense. Is this clear? Anybody is having any doubt, you can ask the question, right? So आपको कब तक चेक करते जाना है? आपको चेक करते जाना है जब तक ये इनफाइनाइट ऑर्डर नहीं हो जाता है. Infinite order strict sense stationarity process. Oh my god, I need to take infinite random variables. Who is going to take that one? I'm not going to take that one, right? So this is why the second order PDF, the second order stationarity, what it says, this, if you see this, go back and check the definition of autocorrelation and autocovariance, function of two random variable. Where it is that? Here it is. This one. So all the properties, all the statistical properties which are dependent on second order PDF, they all are going to be function of time difference, because this is second order stationarity process. If this is a second order stationary process, then I can see that when this PDF, this joint PDF, is not going to function of T1 and T2, but the time difference of T1 and T2. And in that case, if it is a function of only time difference, then any function you define on this two random variable, like we have autocorrelation, autocovariance, they are going to be only function of time difference, not what? So if you say second order stationary process, then I will say my autocorrelation T1, T2 will only be function of time difference. So this is what the meaning is. So if you say, let me write big second order stationarity, it implies if any first, let me write first order stationarity process, higher order implies lower order stationarity, right? So let me write that higher order triple S implies lower order. Anybody can prove this one, triple S, but the reverse is not true. So if any process which is first order stationarity, it may not be second order stationarity. But if it is second order stationarity, then it has to be first order stationarity. But if it is second order, then you cannot say it is third order also. You have to check that one. So higher order implies lower order stationarity, but lower order does not imply higher order stationarity. And we just saw that when the second order stationarity, if we have a strict sense stationarity, then it means it is going to be WSS, because second order implies first order, and first order implies all the powers are going to be constant, means DC value is going to be constant, and second order implies the autocorrelation is going to be independent of time. It is going to be function of time difference only. So this implies WSS, but the reverse is not true. But the reverse is not true. This is only true if the random process is Gaussian random process. So if the Gaussian random process is a WSS process, then it has to be second order stationarity process. So time is up now. So we will end this topic here only. So this classification is going to come in the exam, and one more classification is remaining, which is ergodic process, and that I will take it in the lab. So you can watch this video and the lab video for the classification. What is that? Ergodic process. That is a third classification. So for this you can watch the next video. And one important time from your side, if I get time in the lab, I will discuss this also. That is what? Properties of autocorrelation function. You read it from yourself, the of WSS process. If we are going to consider only WSS process, right? Because as a communication engineer, we only focus on power analysis. So read that one. Read also power spectral density property. So these two things are very important. And जहाँ तक पढ़ाया है मैंने लैब तक, those all topics will come in the exam, right? और जो नहीं पढ़ाया वो नहीं आएगा. So this is what, only two topics are remaining, I feel like, in the third unit, but I touched upon all the topics with very careful selection of top this contents, because they are very important.